Okay class, I'll be handing you an assignment and you will need to answer it and submit it tomorrow.
Yes,
this will
sir.
this will have a big bearing for your final grade.
Oh, man.
Why, sir?
Thank you, sir. Is this hard? Oh, no! This is so hard! How will I answer it? Oh, what's this? Do you want to know the answer? Lovers Lane 1.
You're late. You want some answers?
Answers? Yes, please, give me some answers.
Then first, you shall encounter different challenges. Are you ready?
Yes, I'm ready.
Give me your hand. You have to catch my finger to know the answer.
Okay, yes. Oh no, you're so fast. I won.
Now, I should tell you the answer.
Yes.
For this problem, we're going to need to distinguish the difference of the symmetrical and unsymmetrical beams. Symmetrical beams have their neutral axis located at the center of the beam, wherein the area of the compressive stress and the tensile stress are equal. However, there are materials like iron which has a greater compressive stress than tensile stress. That is why it is desirable to use a unsymmetrical beam wherein the area of the compressive stress or tensile stress is different from each other. Because the unsymmetrical beam provides a stronger fiber located at a greater distance from the neutral axis than the weaker fiber. These are the variables we're going to need for our solution.
Now, you shall meet the point master.
Where's he?
He's over there. Now go.
Okay. You're the one they call the coin master?
Are you sure?
Yes.
If you're sure, then I am the one they call coin master.
What are they gonna do?
You need to guess where the coin is. Are you ready?
Yes. So fast!
Careful the coin. No! You defeated me. Now, you deserve the answer.
Yes.
So, I will teach you now what is a neutral axis and where to determine it. So, a neutral axis can be located at the centroid of a cross-sectional area of a beam. So, in an unsymmetrical beam, the centroid is not always located at the center of the cross-sectional area. Using symmetrical beams gives more area in the compressional part. So, the figure given on your problem, the neutral axis is located here. 180 millimeters below from the lower fiber and 80 millimeters located at the upper fiber. So the upper fiber is weaker than the lower fiber. So that's all.
Now, where shall we go next? You must go to the field and look for Alexis the bus reflector.
Alright.
Hey you! I heard you need some help in your SMAT homework. How stupid!
Please give me, please.
No! You have to beat me first in a race.
Race?
You're too fast for me. You're here are the answers for your SMAT homework.
So I'll now discuss the flexure formula. Flexural stress are stresses that are caused by the bending moment. In this discussion, the notation FB will be used instead of the stress to denote the flexural stresses. So FB is the flexural stress in MPA or in sine. So considering a differential area dA at a distance y from the neutral axis, the force acting over the area is FB times the differential area equivalent to y over rho times the modulus of elasticity times the differential area. And we can rewrite it as the modulus of elasticity over rho times y times the differential area. So the bending moment is equivalent to the integral of y times the force acting over the area, equivalent to the integral of y times the modulus of elasticity over rho times y times differential area. So we can get this equation, the modulus of elasticity divided by rho times the integral of y squared times differential area. But we all know that the integral y squared differential area is equivalent to I, where I is the centroidal moment of inertia in millimeters to the fourth or inches to the fourth. Then, the bending moment will be equivalent to the modulus of elasticity times the centroidal moment of inertia divided by the radius of curvature of the beam, or the radius of curvature of the beam equivalent to the modulus of elasticity times the centroidal moment of inertia over the bending moment. And substituting the value of the radius of curvature of the beam equivalent to EY over FB, or the flexural stress in MPA, so we'll get this relationship: flexural stress in MPA equivalent to bending moment times the distance of a fiber from the neutral axis over the centroidal moment of inertia. So FB max will be equivalent to the bending moment times C, or the distance from the neutral axis to outermost fiber in millimeter over the centroidal moment of inertia in millimeters to the fourth. So you will use this equation to be able to answer the problem.
Oh yes, now I know. Now go meet the rock in the engineering building. I wonder where I can find the rock. Hey, did you just say my name? Oh no, I didn't. I heard you. I'm looking for the rock. Oh yes, I'm looking for the rock. Now battle me with rock, paper, scissors. Okay, come on. Ah, she's the rock. You defeated me. Now I'll show you the answer. Yes.
Figure 5b is made of cast iron, for which the allowable stresses are for tension 40 MPa and for compression 100 MPa. If the properties of the cross-section are shown, determine the maximum uniformly distributed load that can be supported. So this is the given figure, shear diagram with cross-section. To get the bending moment at the distance 1.2 meters, we can use the area method to get the bending moment. So 1.2 meters times negative 1.2 omega sub O will lead us to the bending moment negative 0.74 omega sub O. So the negative sign in the bending moment determines that the tension is on the upper fibers. So by using the resistive moment formula, which is stress times I over Y, we can get the tension, moment tension and the moment compression. So the stress in tension is 40 MPa, then multiply it to I, which is 50 times 10 to the negative 6 over 0.080 meters, because the upper fiber is 80 millimeters. And that results corresponds to 25 kilonewtons times meter. Then to get the moment compression, we use 100 MPa because it is the stress for compression times 50 times 10 negative 6 over 0.180 meters because it is the total height of the cross section. Then the answer leads to, and this equation leads to the answer 27.8 kilonewtons meter. Because the tension is on the upper fibers, we will equate the bending moment to the moment tension. So 0.74 omega sub O is equal to 25 kilonewton meters will lead us to omega sub O is equal to 34.7 kilonewtons per meter.
What now? Now go inside the engineering building and go to the CR.
Oh, the boy CR!
Come here.
I'm the wrestler.
Oh,
The thumb wrestler.
oh no!
Come here inside. Here.
What are we gonna do?
Let's wrestle. Hey yo, you're very strong. Want to hang on to me sometimes?
Oh no, just give me the answers!
Here's the answers.
From the shear diagram, we've seen that the second point of zero shear was at 2.7 meters. Although the moment was lower than the x, so it was to 1.2 meters, the curvature is reversed and is concave upward, placing the upper fibers in compression and the lower fibers in tension. So, using the same equation 5-2, which says that MR is equals to stress times I over Y, we can compute the M sub C. Getting the moment compression, we have 100 times 10 raised to 6, 50 times 10 raised to negative 6 over 0.080 will give us 62.5 kilonewton meters. Okay, the second one was the moment tension. 40 times 10 raised to 6 times 50 times 10 raised to negative 6 over 0.180 will give us 11.1 kilonewton meters. After deriving the M sub C and the M sub T, we have to compute first for the M. Will give us M is equals to 0.405 omega O. We're getting the moment at point x is equals to 1.2 meters, x is equals to 2.7 meters. There is also a point at x is equals to 4.2 meters. So, why is it unnecessary to derive the moment at x is equals to 4.2 meters? So we can conclude that the safest load for this problem was at omega O is equal to 27.4 kilonewton meters, which is the smallest of all.
Now, for the last challenge, we have to meet the boss at the botanical garden. Go now.
Yes! Woo! Are you the boss? Can you finish me my assignment?
Yes, but you must meet first.
Nakaganda.